Hey, Mr. Mias is here. How you doing? Good to see you again. I really can't see you, but you can see me, so good seeing me again, I guess. This is lesson 4-3 for Essentials of Calculus. We're going to talk about concavity and points of inflection. And then in my next video, for the second part of this, I'll talk about the second derivative test for relative extrema. All right, so some people believe the second derivative test is what we do to find inflection and concavity, and that is wrong. It's actually for extrema, but let me talk to you about concavity first. So let me shrink myself down. Okay, here we go. So a graph is concave upward. It's concave up. This is concave up. It's concave upward if tangent lines are below the graph. And if tangent lines are below the graph, that would mean that the slope of the tangent lines are increasing. So I know it's a negative slope, but they're increasing in slope, which means that the second derivative is positive. So concave upward, the second derivative is positive. If it's concave downward, then the tangent lines are above the graph, which means they are starting to decrease as they go from left to right, which means that the second derivative is negative. So another way to think about, to remember what's concave up and concave down in terms of what they look like is smiley face, concave up because I'm feeling up, sad face, concave down because I'm feeling down, concave down, sad face, concave up, up. Smiley face. All right, now that you've seen my face a lot, that's how we could tell if it's concave down and concave up. All right. So if we took a look at this, we'd be going concave down and concave up. It's a smiley face going up, concave down. So a point on a graph where it changes concavity from concave down to concave up, or concave up to concave down, that's called a point of inflection, or an inflection point. At an inflection point, the graph of the tangent line, the graph has a tangent line, so that's important. It means that it's differentiable there, and the graph changes concavity. So from concave up, concave down, concave down, concave up. All right. All right. So this right here, this would be an inflection point because it goes down and then up. Let's take a look at some examples, graphically speaking, anyway. So in this graph here, let's take a look at what intervals are concave upward. Now remember, we're looking for concave upward. We're looking for smiley faces, right? Because we're feeling up. This is concave up right here. So we're going to say from -2 to -1 is a concave up interval. Concave up, smiley face right here. So 1 to 3. And then concave up again right here, from 4 to 5, right? Okay, so let's take a look at concave downward. Concave down is boo, sad face right here. Concave down from -1 to 1. You got to use the noises too, right? Now this section here, this is a straight line. It has no concavity, so we're not going to look at that. And then this is concave down. So we got 5 to 6 is concave down. Where do we have no concavity? Well, no concavity from 3 to 4. Let's use a different color here. No concavity from 3 to 4. And I'm not sure you can tell this, but let me zoom in. There it's, I use the sound effects. Here is part of the graph. You can't really tell, but there is a dark part of the graph. So 6 to 7. 6 to 7. Oops. 6 to 7 is also has no concavity. What are the inflection points? So again, the inflection points have to be a differentiable point that changes concavity. Whoa. You know what that was? That was a bell. An inflection point is a differentiable point that changes concavity. Notice here, this is a sharp turn, so this can't be an inflection point. All right. This right here goes from concave down, boo, to concave up, yay. And this is a tangent line there, so we've got an inflection point at 1, 1. And then again, this goes, that doesn't change any concavity here. This goes from concave up, yeah, to concave down, boo. And then that has a tangent line there. So we're going to say at 5, 1 is our other inflection point. All right, so hopefully that gives you a sense of what we're talking about with inflection points and concavity. Let's take a look at how we do this analytically. So analytically is just a big fat word for, using algebra work, okay, showing work with a function. So analytically, we find concavity intervals by using the second derivative number line. So similar how we did the first derivative test where we made a number line for f prime. We're going to do the same thing. We're going to make a number line for f double prime. And then we're going to plug that in. And then it's going to tell us what's positive and negative, concave up, concave down. Okay, so let's take a look at how we would do this. So we're going to take the derivative. I'm going to get 4x cubed plus 3x squared minus 6x. And then I'm going to take the derivative again, because I need the second derivative. And get that. All right. Then I'm going to set this equal to 0. And I'm going to factor this bad boy. 2x minus 1, x plus 1. So I'm going to get x equals 1/2 and x equals -1. Now we also have to determine if there's any places where f double prime is undefined. Are there any places? No, it's a polynomial, so great. These are our possible inflection points. Possible inflection. Possible inflection. So I'm going to call them there my possible points of inflection, my PPIs. My PPI. Possible points of inflection. So at x equals 1/2 and x equals -1. We're going to make a number line for f double prime. Look at that. I'm going to be a mathematical rapper here soon if I keep rhyming. Okay, so we're going to plug in a number here. -2. We're going to go and plug it into our second derivative. I'm going to get a negative and a negative, which makes a positive. I'm going to plug in, let's pick 0, plug that guy into my second derivative. That's going to give me a negative times a negative times a positive, which is a negative. And then pick a number over here, and we're going to get positive. So what does that tell me? That tells me for my f graph, for f, it's going to go concave up, concave down, concave up. All right? Up, down, up. So I'm going to go ahead and write these down. I'm going to put that concave up on the intervals from -infinity to -1 and 1/2 to +infinity. Concave down from -1 to 1/2. Now we needed to find inflection points, so we've got a value here at -1. It does change, and it does change here. So we're going to have our inflection points, or points of inflection, however you want to say it. Not private investigator. We're going to take -1, plug that back into our original function to get our y value, which is going to be -2. And then we've got one more. We're going to plug in 1/2 into our original function to get our y value, which is 7/16. All right. Points of inflection, guys. Let's take a look at one more example. Shall we? Sure. I'm making this video, so we might as well. If f of x equals x squared plus 1 over x squared minus 4, and f double prime, oh, look at that. We already have the second derivative. Isn't that nice and helpful of them to give us the second derivative? We don't have to do the work. Look, guys, if they give you the second derivative, don't try to do the second two derivatives. They already give it to you. All right? List the intervals where the graph of f is concave upward, concave downward, and list the points of inflection. So what are our PPIs? Our possible points of inflection, or possible inflection points. We could call them pips, right? What are the pips? What are my pips? Okay. Well, we have, doesn't look like we have anything in the numerator that could set, that we can set that equal to 0. So, we have some things that we need to consider. The domain is x cannot be equal to negative plus or minus 2, right? If we set f double prime equals 0, there's nothing to solve. So I guess we're not going to have any real possible points of inflection because we don't have any derivatives there to solve. So all we have to deal with are these domain restrictions, which in this case, since they're in the denominator, we're going to end up having some vertical asymptotes. So let's go ahead and draw our number line now. Our f double prime number line. Excuse me, our f double prime number line. -2, +2. Okay, we'll put negative 221. Sure. Negative 221 in there. It's going to give me a positive on top and a very positive on the bottom. So that's going to be positive. And then this guy right here is an asymptote. So I'll put my dots here. 0 is going to give me, let's see, a positive divided by a negative. So that's negative. And then 232 is going to give me a positive. Guys, you can pick anything. You can pick -3 if you wanted to. Again, we don't really need the value. All we need is the sign. So we've got concave up, smiley face, concave down, concave up. All right. A bit bipolar there, right? Smiley, frown, smiley, frown. Okay, so when are we concave up? Concave up, -infinity to -2. And 2 to infinity. Concave down. -2 to 2. Do we have any inflection points? No. No inflection points. Because, well, we don't have any time when f double prime is equal to 0. We just have the domain restrictions. All right. So there are two examples of sorry, guys. Can't speak. My spoken is incorrect. Those are two examples of how we would use the second derivative to determine the inflection points and where our graph is either concave up or concave down. There you go. We'll see you soon.